Good afternoon, dear students. Yesterday we have seen the ideal gas equation. Today we are going to see about the deviation of ideal gas. How it's deviated, why it deviated. What is the reason for the deviation? That is what we are going to see now. Then one by one we can see. Deviation of ideal gas. So what is the ideal gas equation? PV equal to N0. According to this ideal condition, the total volume is greater, so individual volume is negligible. First assumption. Volume of individual gas molecule is neglected. Then, so volume is neglected means there will be a pressure, no force of attraction. Attraction between molecules. To achieve this, the gas which obey these two assumptions, they can behave as an ideal. Okay. But in practice, if you say in practice, there is no possible at all to obeying these two assumptions. For example, if you say liquefaction of gas, if you take the liquefaction of gas, when the gas is liquefied, there is a force of attraction. So, there is no chance for the ideal gas. Ideal gas, there will be in the practice, there is no chance. So the gas which is not obeying this rule, all are called as a real gas. So, but at a certain condition, temperature, pressure, there may be possibility to obey this assumption. Okay, not always, but at a certain time, at a particular temperature, at which the real gas behaves ideally is called a boil temperature. Boil temperature or boil point. The temperature at which the real gas behaves ideally at certain temperature. Okay. That a temperature is called a boil temperature, or that particular point is called a boil point. Okay. Then, what is the optimum condition for the ideality? For ideal gas, low pressure, LP, at high temperature. This is the ideal condition for when a gas behaves ideally, most probably. We cannot say accurately, but the gas tend to behave ideally at a low pressure and a high temperature. Okay, at low pressure and high temperature. Then I need to give an explanation why at low pressure and high temperature the gaseous molecule is behaving ideally. First take at a low pressure. At low pressure what happened? Low pressure. Normally at a low pressure the volume of the container will be large, greater. Volume of the container will be greater. You consider this is a gas molecule. At a low pressure, the volume of the container will be larger. So inside the particle, maybe for this assumption value, maybe 10 particles are there. It will be roam around here and there. So the volume will be reduced. Volume of the individual gases will be reduced. It will go away. Split into that. Then the force of attraction, automatically at low pressure, the force of attraction between the gaseous molecule will be reduced. See, if all those molecules very close to each other, there will be a force of attraction. But the volume of the container is maximum, greater at low pressure. Then the gases far away from each other. So the force of attraction between the molecule is force of attraction decreases when the distance increases. Okay, that's why at low pressure. So low pressure it is obeying this assumption. Volume of the gas is neglected and the no force of attraction. So at low pressure they tend to behave as an ideal. Then at what were high temperature? At high temperature what happens? The same explanation we can give. At high temperature, kinetic energy of the molecule increases. At high temperature, when a temperature increases, kinetic energy of the molecule also increases. Kinetic energy of molecule also increases. When a kinetic energy of the molecule also increases, then they will go away from each other. At high temperature, if we consider the 10 molecules, they are far away from each other. Okay, so automatically there is no force of attraction. This also obeying this condition. So what happens when the pressure increases, sir? At high pressure. At high pressure again, pressure increases, volume automatically decreases. All those gaseous molecules are very close to each other. All those gaseous molecules are very close to each other. Then at high pressure, the molecules are close to each other. There is a possibility of force of attraction between these two molecules. So they are deviating from these two assumptions. Volume is considered and the force of attraction also is there. So at high pressure, normally the real gas ideal gas tend to deviate from the ideality. Then what happened to the at a low temperature? Low temperature what happens? As usual, at low temperature, when the temperature decreases, kinetic energy of the gaseous molecule also decreases. Kinetic energy of the gaseous molecule decreases, then force of attraction. Kinetic energy decreases, the movement of the force of interaction also increases. Kinetic energy decreases, the distance between the molecules decreases. Automatically, the force of attraction between the molecule increases. So they are deviating from this. So what is the optimum condition if we say for the ideal behavior? Low pressure and high temperature. So this is how the gases are deviating from the ideality. Okay. Now we are in the position to measure the deviation, how they are deviating. Like that, the measurement of deviation should be done. For this, we have a factor, that is a Z factor, compressibility factor. Compressibility factor denoted by Z. Compressibility factor, it is nothing but it is measure of deviation of ideal gas from the reality. Let us move on to the compressibility factor Z. It is denoted by letter Z. Compressibility factor we can define from this ideal gas equation PV equal to nRT. Okay, you know very well this is ideal gas equation PV equal to nRT. Then the compressibility factor is nothing but PV by nRT. That is equal to Z value. It is a scale to measure the deviation. That I have said. So what happened? The Z value equal to 1. If Z equal to 1, then the gas behave ideally. If there is increases or decreases, it may be Z is greater than 1, then there will be deviation, that is a positive deviation. Z is greater than 1, that is a positive deviation. When Z equal to less than 1, there will be also deviation, that is a negative deviation. That is a negative deviation. So the Z is a compressibility factor. It can be measured from the ideal gas equation PV equal to nRT to Z. Okay. Then at a positive deviation, what happens to the pressure? Pressure will be high pressure. Likewise, at a negative deviation also, you will have a low temperature. Pressure variation, temperature variation is there. Okay. That is a Z value. Then for the graph between the Z value and pressure. For ideal gas, the graph is straight line. It's given straight line parallel to this axis at various pressure. This is condition Z equal to 0. Sorry, Z equal to unity, that is 1. for the ideal behavior. We have a graph for a few natural gases. For nitrogen, for a hydrogen, for helium, for hydrogen it will be, for carbon dioxide, methane it will be like this. This is for carbon dioxide. So the graph is that, or in some book you may see that PV by nRT. So what it means, this is low pressure, it may be 0 if you take, this is your low pressure, they are behaving as ideally. If pressure increases, they are deviated. It is more deviated, there is a positive deviation. Below this line are negative deviation. This is positive deviation. So Z value greater than 1, whereas Z value less than 1. We look at the graph, this may be clear with it. Okay. Then one more graph is there, that is we can in the book we can see the colored graph here. I cannot show in the book board itself. There particularly nitrogen they have taken nitrogen different temperature with various pressure graph will be there, that will be shown in the book. You can see individual gas nitrogen alone they have graph is plotted. Okay. Then let us move on to the Z value for real gas. Okay, Z value for real gas. So PV real by nRT. PV real by nRT. Okay. So you know very well what is the ideal gas equation. PV ideal equal to nRT V ideal, what will be V ideal equal to nRT by P. We can write like this, V ideal equal to nRT by P. Okay. Then for our convenient purpose, I am 1 by V ideal. What will be 1 by V ideal equal to P by nRT? You can write like this or not? V ideal will be nRT by P. The 1 by V ideal that is equal to just invert P by nRT. You can write no. Right. Then if you see, we need this area P by nRT. We is needed no. So we have data for P by nRT. Just you substitute there. You have this equation number 1. You have this equation number 2. You substitute 2 in 1. Equation 2 in 1. What is the equation number 1? Z real. That is equal to P by nRT. P by nRT, that is equal to 1 by V ideal. And remaining V real. So that's all about the derivation we got. Simply we can write Z factor V real by V real by V ideal. Here V is a molar volume of the real gas and ideal gas. By using this data also we can calculate the Z factor. So already we have one formula for Z factor. This is for real gas. By using the V volume of the real gas and volume of the ideal gas, there also you can calculate the Z value. These are about that compressibility factor. Compressibility factor is nothing but it is a measure of deviation from the ideality. How is it deviated? If compressibility factor Z value equal to 1, that is ideal. It is very difficult or impossible to get But sometimes some gases behave ideally at a certain temperature and pressure. That temperature is called a boil temperature, or the particular point is called a boil point. Okay. Above the boil point there will be a positive deviation. Below the boil point there will be a negative deviation. This is a calculation to the compressibility factor for real gases. Okay. From the volume we can calculate that compressibility factor, or otherwise pressure volume negative. Okay. Then let us move on to the van der Waals equation. Okay. Let us see the van der Waals equation. Okay. So already we have ideal equation. What is the ideal equation? PV equal to NR. Let it be PV equal to NR. The van der Waals is shifting to the left. That is already practice. It is not possible to reach the PV equal to NRT. So we are saying that the real gas are deviating from the ideal gas. So van der Waals shift and experimented many things and finally got that some alteration in that ideal gas equation. How the real gas for real gas, how we can write this equation, gaseous equation, how we can substitute. Simply if you write like this, it is error, no, because we cannot reach this condition. So he do some alteration in this. What are the alteration he has done? First of all, the trouble is in a pressure and volume. He made two corrections. One is a pressure correction, another one is a volume correction. Pressure correction and volume correction. After this correction, he altered the main gaseous equation. Okay. Now let us see the pressure correction. Now what happens to the pressure correction? Oh, pressure correction. Okay. If you see the container, just I am imagining that there are two particles. With the gas mixture, number of particles will be there. For your understanding purpose, I am writing A and B, two particles are there. Okay. What is the pressure? The forces exerted by the gaseous molecule towards the container, volume of the container. Total volume, this is total. This is force. This is force by A, and the other forces by B. This is also hitting towards the or bombarding towards the container. Okay. A. This is the dotted lines of B. During the bombardment, the force is disturbed. Okay. So total force is disturbed. We are assuming that the pressure of the container only. For here, the equation P will be taken like this. If you take the pressure like this, what happened to that? There is a decreased amount of pressure. Pressure is reduced. Why pressure is reduced? During the bombardment, there is an interaction between the A and B. There is an interaction between the A and B, or otherwise we can say that the bombarding time or hitting time is restricted by A. The same way, B also restricting the bombardment or hitting the walls. The force of attraction disturbed by the B. That is called a force of attraction between the A and B. Thus, the net pressure, there will be a reduction of pressure. Pressure, surely, if I think pressure is 2 atmosphere, for imagine, I am expecting is 2 atmosphere. Actually, if I write 2 atmosphere, that is not so. Already, few pressure is used for this interaction. So, actual pressure should be greater than that of the observed pressure. That is, he found that the pressure should be added. There are few force of interaction that is disturb the. What is the pressure? Pressure is nothing but the force exerted by the gaseous molecule inside the compartment. But the actual force exerted by A is not so, because it is disturbed by the molecule B. So already the force, the measured total out forces will be very less to observe. So we need to add some factor to the pressure observed. Actual pressure should be something above than that pressure. How we can measure? He found that pressure is directly proportional to square of the density. Square of the density. Square of the density. You know very well what is the density. Density equal to number of moles by volume. That you know very well. Okay. Now you substitute this one. Rho is N by V, rho squared. So pressure is directly proportional to N squared by V squared. We can write. Then to remove the proportionality, we need a constant, that is P equal to A N squared V squared. A is a proportionality constant. Here the A used by van der Waals, so we can have A is a van der Waals constant. So this much amount of pressure is restricted. So we need to add this much amount to the total pressure. So what is the pressure of ideal pressure? Real pressure we are what is the pressure of the container, but ideal pressure should be like this. Already the real pressure plus A N squared by V squared. Okay, this is a pressure correction made by van der Waals. You are getting me or not? Just you listen this. Once again I am explaining. The gaseous state somewhat difficult to observe. If you observe the point properly, then it will be easy. When you lose the observation, that's all about this. Nothing, so you cannot memorize all those things. How many times if you memorize and also you may go wrong. But you should understand the concept first. What happened? Just consider the two particles, A and B. They are exerting force of attraction towards the container. So this is the pressure of the container, we are assuming that. But actually what happened? There may be a force of interaction between the A and B. Because of this action, the pressure may be reduced. The reduced pressure should be added to the overall pressure. That we have done. You get that? It's added. So after the so many experiments, he got that the density of the gas is directly proportional to the pressure. That is, the square of the density of the gas is directly proportional to the pressure. So density rho equal to N by V. N is number of moles by volume. If you apply that N squared by V squared, that is directly proportional to the pressure. To remove the proportionality constant, we are adding A. A is a proportionality constant. Here van der Waals is used to A, so A is a van der Waals constant here. This much amount of pressure is we are left from the overall pressure. So we should add this pressure towards the pressure. So the pressure of ideal gas P, there is absorbed pressure, then plus A N squared by V squared. A is a constant. For A value will vary for particular gases. N is a number of moles, V is a volume of the gas. Okay. Now let us move on to the volume correction. So what are the trouble from the deviation from ideality? Pressure and volume. If there is not exact pressure, there is not exact volume, so that only all the gases deviating from the ideality. That way van der Waals sit and experimented and find the pressure correction. Then for volume correction. Volume correction, we are considering the volume of the container only. If your gas molecules are present, simply what we do, we are containing the volume. If we consider 1 liter, if you take a 1 liter container, you say volume, what is the volume of the container? 1 liter. It may be right or wrong. The actual volume will be something less than that of our assumption. See, two gases. I am considering two gas molecules A and B. Okay, but actually the volume of the container will be large like this. So we have assumed that the volume of the container like this, but the original volume is this only. So what to do to avoid this error? The volume of the container, we take total volume of the container, but individual gases molecule comparatively very small than that our assumption. So this will be like this original volume, but we are assuming that this much volume. This is a 2R. So in order to balance this, we need to subtract some factor towards the volume observed. How we are adding this some factor towards the pressure. Likewise, we need to subtract some value to the volume. So for this we are, what is the volume? Volume equal to 4 by 3 by R cube. Here if I, for the two molecules, R equal to 2R. If we substitute that R equal to R, V equal to 4 by 3 into pi 2R cube. So what will happen? 8 4 by 3 by R cube. Okay, this is a excluded volume. Volume of, excluded volume of 2. So this can be Vm, volume of the molecule. This is excluded volume. So we can, how we can write 8 Vm we can write for excluded volume. Excluded volume is 8 Vm, because Vm equal to 4 by 3 by R cube. Here 8 times of Vm, so excluded volume is 8 by. This is for a consideration of two particles. So excluded volume for two molecules. We have excluded volume for two molecules. Then what for one molecule? Excluded volume of one molecule. For 2 8 Vm, no. For 1, what will happen? Divided by 2. That 4 Vm. Excluded volume 4 Vm. Then excluded volume for n molecule. Because gas is mixed containing n number of gases for only 2. For the explanation purpose, I am taking 2, 3, 10, 4 like this. But the gaseous mixture contains n number of molecules are there, particles are there. So we need to calculate the excluded volume for the n molecule, n number of molecules. So if we go for n number of molecules, what will happen? N into 4 Vm. This is a excluded volume for a n number of molecules. So 4 Vm, water was given a constant 4 Vm equal to B. This is a constant given by van der Waals. Okay, instead of the 4 Vm, we can put a B. So excluded volume N B. Okay, because we were substituting 4 Vm equal to B. B is a van der Waals constant, so Nb. Okay, this is called a excluded volume for N molecule. So what is the volume of real? If we go volume of real, volume of ideal, not real, ideal gas equal to already observed volume. This should be neglected. That is excluded mean we should omit this. So subtract this Nb. So finally this is volume correction done by van der Waals. So once again I am saying this, van der Waals finds that there are some few error and correction in a pressure and volume. So pressure is some pressure we are not adding, so we need to add. The explanation is given. So what much amount of pressure should be added, that is we calculated, that is AN squared by V squared. So pressure of ideal P plus AN squared by V squared. Likewise volume we need to exclude. Here pressure need to be included, whereas volume need to be excluded. So we need to find out how much volume should be excluded. For the derivation we have put for 2, then 1, then n. We finally got a x volume of ideal. This is volume of ideal. This is volume of pressure of ideal. So you combine to both in an ideal gas equation. What is the ideal gas equation? PV equal to nRT. PV equal to nRT. So for ideality, we need to take ideal pressure. What is the ideal pressure? P plus A n squared V squared into, what is the ideal volume? Ideal volume is here into V n minus V, that is equal to n RT. This is van der Waals equation. We read again the top. We may doubt. So what is the correction in pressure? P plus A n squared V squared into V volume correction NB, this is equal to NRT. This is van der Waals equation, or third van der Waals equation for the. Once I am repeating how van der Waals equation is derived. You know very well, van der Waals is from the ideal case, he is doing some alteration. PV equal to nRT, ideal case equation. Okay, right? Then, after some assumption, they got that there is a pressure variation and volume variation. It should be corrected. If we correct those things, the equation may be adapted to all the real cases. Okay, all the real cases, it is very close to the ideality. So he did some experiment to find the where we need to do the correction, pressure and volume. So first we are going for the pressure correction. Pressure correction, after doing some experiment, the derivation we are getting that A n squared by V squared, that is a pressure correction. That is pressure should be included. Okay. We are not assuming in the ideal gas equation, normal ideal gas equation, we are not assuming that extra pressure that we need to be considered. So pressure, ideal pressure should be P plus A n squared V squared. Likewise, in volume. Volume we are assuming that enlarged volume, not actual volume. So we need to find the actual volume. So we need to subtract some factor towards the actual volume. For this we are doing this, for this 2 and then for 1 molecule, then for n molecule. The n molecule 4 Vm, that is, the question may be asked, what is the excluded volume for 1 molecule, 4 Vm? What is the excluded molecule volume for 2 molecules? If you ask 2, 8 Vm. They may ask, neat question they ask, what is the excluded volume for n molecule? N molecule is, that is equal to n into 4 Vm. N into 4 Vm is nothing but a NB. B is a constant for the 4 Vm. B equal to 4 Vm. This is a constant given by van der Waals. So finally, volume of ideal gas equal to V minus NB. So he is substituting towards the PV equal to nRT, then you are getting that van der Waals equation. P plus A n squared V squared and V minus NB equal to nRT. This is a van der Waals equation. I hope that you understand van der Waals equation clearly. Thank you.